section provides a brief introduction to normalization of databases. This brief presentation was organized by Dr. Lemmy and narrated by Samantha Tone. The objective of this lecture is to learn about rules of good design. If the database is not well designed, then updates, insertions, and deletions could lead to anomalies in the data structure that can make the use of the database difficult. Normalized design improves efficiency, allows faster processing of the data. It reduces redundant data or data entered in different places. It reduces the need to enter missing data for a situation where the data entry is not appropriate. For example, since a pregnant male is not possible, we would like to have pregnancy information kept in a different table than gender information so that we do not need to enter blanks for pregnancy field for males. Good design allows users to manipulate the database without knowing the physical location of the data. It should be possible for a user to search for a piece of information in one field and not have to guess what other fields may contain the same information. Update anomaly refers to a situation where the same information can be expressed on multiple rows, therefore updates to the table may result in marginal inconsistencies. For example, each record in an employee skill table might contain an employee ID, employee address, and skill. Thus, a change of address for a particular employee will potentially need to be applied to multiple records, one for each of his skills. In this example, one's for public speaking and another type of carpentry skills. If the update is not carried through successfully, if that is, the employee's address is updated on some records but not others, then the table is left in an inconsistent state. Specifically, the table providing conflicting answers to the question of what this particular employee's address is. Insertion anomaly refers to circumstances in which certain facts cannot be recorded at all. For example, each record in a faculty and their courses table might contain a faculty ID, faculty name, faculty hire date, and course code. Thus, we can record the details of any faculty member who teaches at least one course. We cannot record the details of a newly hired faculty member who has not yet been assigned to teach any courses, except by setting the course code to null. This phenomenon is known as an insertion anomaly. Entry in the course table requires knowledge of a faculty member who may not even be hired yet. There are circumstances in which the deletion of data representing certain facts necessitates the deletion of data representing completely different facts. The faculty in the courses table, described in the previous example, suffers from this type of anomaly. For if a faculty member temporarily ceases to be assigned to any courses, we must delete the last of the records on which that faculty member appears, effectively also deleting the faculty member. This phenomenon is known as a deletion anomaly. In these slides, we will review several rules for normalization. Normalization is the process of applying principles to design to data structures so that they conform to our expectations. The first rule we would like you to remember is that each table corresponds to a single entity or a single relationship. You cannot have a table containing information about both the patients and the providers. Doing so unnecessarily adds confusion about where data might be found. It also forces us to add provider information when adding patient information, increasing the redundancy of the data. Always ask yourself what the table is about. If you can tell it is about one entity and one entity alone, then you are on a good start to design of databases. The second rule makes sure that each row in the table is the occurrence of the entity and nothing else. A row in a table is often referred to as a record. Every record should be an occurrence of the entity. So example, in the patient table, each record should be one patient. In the provider table, each record should be a provider. This seems like a very simple rule, but I have seen it violated. Consider a table of visits. Each record should be about one visit. I have seen occasions where multiple records are given to the same visit, or some records in the visit table are about the provider's characteristics. These are not reasonable ways to construct a table. Always check the rows of the table to see that each is an example of the entity. The third rule makes sure that the primary key uniquely identifies the occurrences of the entity. If we know the primary key, we should know which row in the table is involved. A primary key should not be used for two rows in the same table. For example, first name and last name are often insufficient to uniquely identify a patient, as many patients have the same name. But a combination of first, middle, and last name and date of birth might uniquely identify the patient. A social security number uniquely identifies the patient. Rule 4 is to make sure that all fields in the table are facts about the primary key. If the fact is about something else, it does not belong to the table. For example, a name belongs to a table about patients. It is a fact about the primary key that reflects individual patients. Likewise, date of birth is another fact about the patient and belongs to the table. But is diagnosis a fact about the patient? At some level, yes, but in reality, it's not just about the patient. A patient may have many different diagnoses at different times, so in reality, diagnosis is a feature of the patient's visit and not really the patient. It is not a persistent fact about the patient. Therefore, diagnosis belongs to the table of visits and not to the table of patients. Rule 5 is to make sure that we do not present a fact more than once anywhere in the database. Many students think that data should be presented in the sequence found or reported so that it is convenient to use the data. But standard query language makes all data in the database available at all times. There is no need to duplicate the information. For example, it is not reasonable to list the name of the patient's provider in the visit table when the name is available in the provider table. We collect and often report who took care of which patients, but the information gets stored in different places. It is comfortable to have everything we want in a table. It feels that the data is accessible. But in reality, we are talking of a machine, and all data from all tables are accessible. Therefore, there is no need to duplicate the data. We can avoid the error we just talked about by putting tables in the first normal form. A table is said to be in the first normal form if and only if all fields contain only atomic values, and there are no repeating fields in a row. By atomic, we mean that it is not composite of two facts, e.g. total charges in composite of hospital and outpatient charges, and cannot be a field in a table in first normal form. By non-repeating fields, I mean that the same information should not be stored in two different fields. In the previous table, household residents were listed in two fields. The first normal form does not allow this. For another example, if the patient has two diagnoses during a hospital visit, it is not reasonable to list them as 5 fields in the same table. In these circumstances, the recommendation is to list the code that points to a different table that lists the diagnosis as 5 separate records in the table. The point is that the first normal form does not allow any repeating fields. Notice that each employee corresponds to a single row. Because an employee can participate in more than one project, you have to put in a few cells more than one project and their time. Notice that the table lists the projects of Sean in one field. Not a big deal. As a human, you can still read most information from the table and answer this question. Now imagine that you are a computer. How can you tell that P31, P32, P34 means 3 projects? First normal form is violated in this table. When a database table does not have repeating groups, it is in first normal form. In other words, each cell stores only one value. You notice that in this table, some information is repeated, such as employee ID, name, and so on. So this table is not good enough, but it is still better than the previous table because at least some simple questions can be answered. The discussion of the second normal form requires us to introduce the concept of dependency. An attribute y is functionally dependent on an attribute x if a value for x determines a unique value for y. X may be a set of attributes or a single attribute. We show this as an arrow going from x to y, and read it as x determines y. For example, we could say that an employee number functionally determines the employee name. This is the same as to say, if we know the employee number, we will know his name. The reverse is not always true. Knowing an employee name is not sufficient for guessing the employee number. So employee name is functionally dependent on employee number, but not vice versa. We need one more definition before we can state the second normal form. We say that an attribute is fully functionally dependent on another set of attributes, if and only if it is not dependent on any smaller subset of attributes. An employee number may be fully functionally dependent on employee name and date of birth, as it is not dependent on either the name or date of birth by themselves. In this example, employee name is not fully functionally dependent on the attributes employee number and department, as it is functionally dependent on just employee number. Just knowing the employee number by itself is sufficient to know the employee name. We do not need the additional information about the department. In essence, a fully functional dependency is the smallest subset needed to establish functional dependency. In this example, ask yourself if street name is fully functionally dependent on employee ID. It's not. If we knew the employee ID, we still do not know where he lives. We would need to know both employee ID and address type to know where he lives. Now we are ready to state the second normal form. A table is in second normal form if and only if facts in the table are fully functionally dependent on the primary key. This is a very important principle. It says that the primary key is the minimum subset necessary to determine each fact in the table. Here is an example of violation of second normal form. Employment and address cannot be in the same table, as the ID does not fully functionally determine either one. In two separate tables, this is not a problem. The third normal form focuses on whether combination of facts can determine another fact. A table is in third normal form if and only if there are no combinations of strictly informational fields, i.e., not the primary or foreign keys, determines the value of another field. A table is in third normal form if and only if normalization is the process of applying principles of design to data structures so that they conform to our expectations. In this lecture, we discuss 3 additional rules that are used as part of putting a database in normal form. Database design is more than listing of fields and includes judicious discussions about tables and their relationships. Tables that are properly normalized can be exploited by a wide variety of end users who do not have to be familiar with the structure of the data. We provide 5 rules of design and 3 principles of normalization that we encourage you to follow. Normalize data structures to improve efficiency.